Welcome again, dear students. Last class we discussed the kernel of homomorphisms and provide some examples. Also we discussed the when the homomorphism is monomorphisms and epimorphisms. In this class we discuss some properties of homomorphism. Let's begin with the properties of a homomorphism. So we just start with let G and G1 be a two groups. G is under the binary operation a star and G1 is the under the binary operation of this dot circle. And we are assuming that this map phi from G to G1 be a homomorphism, then phi of E is equal to E1, that means where E is the identity of a E is the identity of a G and E1 is the identity of a G1 respectively. Means we have to simply say that if we have a some identity elements here, this is the element of a G and this is the element, this is the set of a G1, and then there is all the elements are there as a sum of E is there, then the map is phi this phi's map is here, and then here is some other element, this is the element of a E1, and that we can say that this is mapping to E1 is nothing but is equal to this E1 is nothing but equal to same as a phi of E. And the second one we can say that if phi x inverse is the same as a phi of x inverse. So, this means if we have a all the elements are here, then we have a some x is there as the inverse of x is also here. So, we have to say that this is the inverse of this map from here is nothing but is equal to, if you have a C like this, we have to this is x is there. So, this is somewhere is a mapping into this is equal to phi of x is there. So, this is you have a inverse of this is phi of x inverse to this phi of x ka whole inverse. That means we have to say that this is phi of x and phi of x ka inverse is equal to identity E1. Yani if we say that if x is mapped to the phi of x, then phi of x inverse should be mapped for the phi of x ka whole inverse. So, this is equal to this thing. And the third one we have to saying that the kernel of this phi is nothing but is equal to is a subgroup of a this G. And if it is subgroup, then we have to show that next is a kernel is a normal subgroup of a G. Then if it is subgroup, then we have to show the normality, and also we have to show that the homomorphism phi x to the power k is the same as a because this can be if you see by the definition of this, you can say that phi of x y, if it is a homomorphism, can be written as phi of x, phi of y by the composition. Now, this can be written as x to the power k x x x up to x, you have a k times, and then we have to write by the using the, because is a giving is a homomorphism, this is a phi of x into phi of x, and this again you have a k times, and this is the same as a phi of x to the power k. Similarly, for all integers. So, this means if it is true for all integers, then again we have three cases are there. If we have a k is equal to 0, k is greater than 0, and k is less than 0. And finally, we have to say that if x is the any element of a this group G, and order of x is equal to n, this means x to the power n is equal to, you have an identity, then the order of this phi of this must divide n. So, this means order of phi of x to the power n is also must be divided this order of this x is there. So, one by one we try to give to the proof of this. First one we have to try this first one. So, I just take a start with the first one. So, let phi from G to be homomorphism. If it is homomorphism, then we have to phi of E is equal to E1, where E and E are the identities of a G respectively. We have to try to prove that phi of E is equal to E1. So, E is the identity of a G and E1 is the identity of a G2. G1. So let E be the identity of a G, and now know that the property of identity is saying that E composition E is equal to identity. Now because this map is giving you have a homomorphism, so phi of E can be written as a phi of E composition E, and then by the homomorphism thing we can say that phi of E and then composition of a binary operation of a G1 is equal to phi of E. Again we have to just say that because you know that E1 is the identity of a G1, so E1 is the identity of a, you have a G1, then phi of E is the element of a, again is a G1, so you have a phi of E composition of E1 is equal to, you have a phi of E1 sorry phi of E, and vice versa this can be written also, this can be written as a E1 this composition of a phi of E. So now we use this, by this we can say that now we have to just say this phi of E is equal to be written in the form of a phi of E and then composition of a phi of E, and now phi of E is the element of a G1 and E1 is the identity of E1 is the identity of a this G1. So E1 is the identity element of a G1 and phi of E is the element of a some G1. So this means we can say that by the property of identity E1 and then you have a composition of a phi of E is equal to, you have a phi of E, and this is the same as you can say that phi of E composition E1. And now phi of E is the same as this thing, so we can write in the form of a this. So you have a phi of E composition phi of E is equal to phi of E is the same as we have a E1 composition of a phi of E, and now by because these are the G1 is a group under this binary operation, that means both the left and right cancellation are hold. So by using the cancellation law we can say that phi of E can be nothing but equal to phi of E1. So we prove that if we have any two elements we taking into this form, and then we can easily prove that phi of E is equal to E1, that means identity elements of a map into the preserving this identity element into this form. So this complete the proof of the A part. We prove that if it's a homomorphism, then phi of E always is mapped to the identity of E1. This is the same as a E1. So now we have to just tuning into this, and then by the cancellation properties we can say that this is equal to. Now we have to try to prove that this second one, and now this second one we can proving this. So let's prove the this second one is saying that phi from G to G1 be homomorphism, then this thing. So we have know that you know that if A composition B is equal to identity is equal to, we have a B composition A, then we simply say that A is nothing but is equal to same as a B inverse, or B inverse A is the B is the inverse of A, or simply is this. So using the same technique here, because we have to proving this is equal to phi of we can try to this phi of x inverse, and we have a phi x composition is equal to identity of because these are the composition here this. So this is identity of a E1, and then this is the same as we can show that phi of x and to composition of a this phi of x inverse. If we show that this thing, then we can simply say that this is phi of x inverse is nothing but is equal to same as a phi of x ka whole inverse by the property of a inverse. So that means we have to try to this thing, because we have to try to phi of x inverse and composition phi of x, and now because you know that this phi is a for all x is the element of x is the element of a G. So we can see this phi is a homomorphism. So if phi is homomorphism, this can be written as a phi inverse x into x, and now x is the element of a G, then x inverse is also the element of a G, and x inverse x is equal to, you have a identity, this can be written as a phi of E, where E is the identity of a G, E is the identity of a G, then this is nothing but is equal to E1, where E1 is the identity of a G1. By the A part we have to prove in this. So, we have to show that clearly phi of x inverse composition phi of x is the same as a phi of x inverse x, and then we have to show that this is equal to identity. Now, we have to again say in the phi of x composition of this phi of x inverse, and this can be written in the form again by using the homomorphism. We can say that phi of x and then we have to using the composition is a star, and then we have a x inverse. Here is also we have a star, and this we have again by the using this is equal to phi of E, and this is equal to phi of E is equal to E1 by the previous part. So, we have to show that clearly phi of x, and then we have a composition of this phi of x inverse is equal to E1 is equal to phi of x inverse composition phi of x. So, now by the using the property of this inverse, we can say that so this means can say that we can simply say that phi of x inverse is equal to phi of x ka whole inverse, that means preserving the inverse also this phi. So, this complete the proof of the second part. Now, we to try to prove the next part is the third part is saying that if we have a this I just say that this I already explain you, and now we have to try to show that phi from D to G homomorphism, then kernel of is a subgroup of a G. So, first we show that you know that the kernel of phi is equal to nothing but is equal to you have x is the element of a G, then phi of x is equal to you have a identity of a this is equal to E1. And now, because G is a group you now is giving, so this E is the element of a G, and then phi of E is also this, because we have to prove that is nothing but is equal to E1, and this is E1 is the element of a identity element of a G1. So, this means in the kernel at least E1 this E1 is the element of a this means you have a E is the element of this kernel, and then you can say that identity element that is a kernel, then the kernel is not equal to. So, we can say that is equal to this, then we have a clearly we can say that where E is identity E1 is identity of a G1. So, means at least identity element into the belong to the kernel. So, we can say that kernel of a phi is clearly non-empty. So, now kernel of a phi is not equal to empty. Now, we have to take any two elements A and B are the element of a kernel of a phi, and then we show that A B inverse also the element of a kernel of a phi. If we show the A and B inverse also the element of a kernel of a phi, then we can say that by the subgroup criteria this set kernel of a phi is a subgroup. So, if A and B are the any element of a kernel of a phi, so we take A and B are the element of a kernel of a phi, then phi of A is equal to identity E1, and then phi of B is also the identity of E1. And now, because we have to show that A B inverse, we try to this if we show that that means if we show that phi of A B inverse is equal to identity, then we can say that A B inverse is the element of a kernel of a phi. So, ultimately we have to try to show that this condition A phi of A B inverse is equal to is identity. If it is identity, that means this A B inverse is the element of a kernel of a phi, and in this case we say that this kernel F is a subgroup of this. So, let us try to prove this. So, because A B and we take any two kernels, A is the element of a E1 and B is the element of a this. So, we take a phi of A B inverse. Now, phi of B inverse, then phi of A and phi of B inverse, and now you know that by the using the homomorphism, and then phi of A is nothing but is equal to you have a E1, and then phi of B can inverse can be written as a phi of B ka whole inverse, and this can be written as a E1, and this can be written as a E1 to inverse. And now you know that the inverse of itself is always a itself inverse of a identity is a identity. So this can be written as a E1 composition. This composition we taking this. So this is E1, and this is nothing but is equal to E1. So ultimately we have to show that phi of AB inverse is equal to E1, and if phi of AB inverse is equal to E1, so this implies that clearly AB inverse is the element of a kernel of a phi. If AB inverse is the element of a kernel of a phi, then we can simply say that this kernel of a phi is a subgroup of a group G. So we show that clearly this satisfy the criteria of a subgroup. Under this criteria, we can say that this satisfy this condition. So clearly this kernel of a phi is a subgroup of a this. So that we have a proof this the second one also is equal to true. So this means we have to show that in this way. Then we have to write in this way, then subgroup of a kernel of a, by the subgroup criteria we can say that, so we can say that kernel of a phi is a subgroup of a G. Okay, now next is showing that we have to phi from G to G1 be homomorphism. Then we try to show that kernel of a phi is a normal subgroup in G, and then we have to, if normal subgroup in G, we have to take any two elements of a element of a kernel of a phi, an element of a G. So G, and we have a suppose phi in the kernel of a phi is equal to some H, then G inverse H is equal to is the element of a kernel of a phi. If we show that, then use the property of this, we can easily say that into this form. So according to the previous part, we can say kernel of a phi is a subgroup. So first condition is hold clearly kernel of a phi is a subgroup. Now next we need to show that for any A belongs to the kernel of a phi and G is the element of a G, and then G inverse is also the element of a kernel of phi. If we have to success to prove this, then we can say that the kernel of a phi is a normal subgroup of a group G. Okay, so let us try, because if we have to showing this one, this means we have to try to show that G inverse belongs to the kernel of a phi. The meaning is simply we can say that phi of G inverse is equal to identity of a G1 is equal to I. If we have to success to prove that phi of G inverse is equal to identity, then this say that clearly this G inverse is the element of a kernel of a phi. So let us start from here. So we take a form G inverse. Now phi is giving you from G to G is a homomorphism. So this is giving the homomorphism. This can be written as a phi of G. Then you have a phi of A. Now phi of G inverse. Now A is the element of a kernel of a phi, because we have given this A is the element of a kernel of a phi. If A is the element of a kernel of a phi, means simply is equal to phi of A is equal to identity of a of G1, then means phi of A is the simply is equal to this. So this can be written in the form of a, this form we can write in the form of a phi of G, and this can be written as a E1, and then you have a phi of a G inverse. Now this can be written as a phi of G, and then phi of G composition, this E1 is giving you as a phi of G, and then you have a phi of G inverse. Okay, yeah, now again you have to using the phi of G, and you have a G inverse, again using the homomorphism condition of a phi, and now this can be written as a phi of E, because G is the element of a G composition G. If G is the element of a G, then G inverse is also the element of a G, and you have know that the G inverse is equal to identity of a G. So this means we can say into this form. So we have a ultimately we have to getting this phi of E, this is G inverse phi of E, and now by the part 1 we can say that this is nothing but is equal to is a E1 is the identity of a this set G1. So we simply say that clearly we have to prove that this means we have to this phi of G inverse is equal to identity of a this set is equal to G1. So we can say that this means this implies that this phi of this means if identity, then clearly you have to say that G inverse is the element of a kernel of a phi, and then we can say by the definition of a normal property of a normal subgroup, we can say that simply if this is the kernel of a phi, then kernel of a phi is nothing but is equal to is a normal subgroup of a this group of a this group G. So this is we have to prove this the another D part, and now we have a one more this is clearly we have to write in this form, and then or you can just take a this is we can by this also we can the phi of G inverse if you taking this there is a no need of this, we have directly saying that phi of G is the element of a this is G1, and then phi of G ka whole inverse is also the element of a G1. Then we can say that phi this phi of G and phi of G ka whole inverse is equal to E1. So there is a from here we can directly can say that this is equal to you have a E1. Okay, now there is a no need. This is the another we have to just say that by directly from here to this is we have to get into this one, but from here directly because phi of G is the element of a G1 and phi G inverse is also the element of a G1. So G and G inverse of that element is giving the identity of a that element G1. So this case this is means directly from here also we can say that, and then no need of writing this. So this is from here directly. So we can say that this is kernel of a G, and G inverse is equal to we have a kernel of a phi. This means directly you can just otherwise we have to I prove the this previous one this thing. Okay, now we have a next part is saying that if phi from DGB be homomorphism, then phi x to the power k is phi of x to the power k, where k is any integer. So we have to try to this form is from k is greater than 0, k is equal to 0, and k is less than 0. So we have three possibilities are there, because we have to true for all each and every integer this result true. So if it is true for each and every integer, that means we have to prove that each of this. So we have to first we take a suppose we take a x k is equal to 0, then you have to know that phi of x to the power 0 is equal to phi of x whole to the power 0. Now phi of x to the power 0 is equal to E, and then is to the power is equal to identity, and that is true by the first one. We can say that that means for k is equal to 0, this is a trivial. Now we have to assuming that k is greater than 0. If k is greater than 0, then we can write phi of x to the power k can be written as a phi of x to x into x up to x, that is equal to we have a k times. And now if this is a k times, then we can say that this can be written as a phi of x into phi of x. This is again is a k times. Now we have to say that this is a k times, this means phi of x to the power k if k is greater than 0. We have to k is equal to 1, then this, and k is equal to 0 corresponding to the I just say that to part A, that is trivial. So now we have to try to this for k greater than 0. We use the induction for k greater than equal to 1. The result true for k is equal to 1. If you take a k is equal to 1, then you have a phi of x is equal to you have a phi of x to the power this is equal to 1 to the power whole to the power 1. Now assume that is true up to the n minus 1, then we have to say that this is result true for up to the this means phi of x to the power k minus 1 is the same as a phi of x whole to the power k minus 1. then we try to sort through for all values of this. So this means similarly we can write this phi of x to the power k can be written as a phi of x to the power k minus 1, and then you have a x, and this is nothing but is equal to, by the homomorphism, this is written the phi of x to the power k minus 1, and then you have a phi of x, and then because the result is true for this, this can be written as a phi of x whole to the power k minus 1 into phi of x, and now this can be written as a phi of x whole to the power k. So this can be written is a true in the case of we have a k is greater than strictly greater than 0. So we prove this result by using the induction hypothesis. We have an index k true for k is equal to 1 is a trivial, and then we have to assuming the result is true for k minus 1, and then by using this k minus 1 is true for all k is there for greater than or equal to 1. So this means we can write in this form the result is true for all values of a k is strictly greater than 0. Now we try to prove the same result in the case we have a this k is less than 0. So if k is less than 0, in this case we can write phi of x to the power k can be written as a phi of x inverse and then is to the power k, and then use the property of this. You know that we have a x to the power minus k can be written as a x inverse to the power k. So we can write x to the power k written as a x to the power inverse to the power minus k, and this is the form. So now we have to write in this form phi of x inverse to the power minus k, and now because you know that phi of x inverse this is nothing but is equal to phi of x inverse is equal to this is power of this. So we can write this phi of x is the same, phi of x inverse can be written as phi of x to the power inverse. So this means is inverse is equal to, so this can be written in the form of this. So we can say that if this inverse, so this means it's inverse, that is phi of x to the power inverse into this form, and now again we have to just say that using again from this is phi of this phi of x inverse is the same as a phi of x ka whole inverse, and then we have to phi of x ka whole inverse, and then again use the property of this. We can say that phi of x to the power n, or we can say that some like this, we can take a some n is equal to minus m, and m is some integers, and then we can prove this x to the power m, and then we have to show that minus m, and then this is true for all these things property. So this means we can prove clearly using this property x of inverse is the same as a phi of x ka whole inverse. By using this property, we show that this means phi of x to the power k is the same as a phi of x whole to the power k. So in the case when k is less than 0. So now this complete all the properties of this 5 properties of a homomorphism. These are the basic properties of homomorphism. We using the problems we have to solve into this. Then we have one more is the left. The last one is saying that if phi of phi from G to G1 be a homomorphism, and x is the element of a G with order of x is equal to n. So it means x to the power n is equal to, we have identity, and he said that order of phi x n divide into this form. So we can just prove this because order of x n is equal to order of x is equal to n. So x to the power n is equal to identity, and you know that the property E1 is equal to, you have a phi of E, and phi of E is equal to this can be written as phi of x to the power n, and now the previous result we can say that phi of x to the power whole to the power n, and then we have to show that phi of x whole to the power n is equal to identity, and if a phi of x to the power all the identity, now we have to use the if this phi of x to the power n is equal to identity. If you have a g x to the power identity if and only if n divides k, so this means if a group of order, finite group of order n, then this result is saying that if g is any group of a finite order of n and g to the power k is equal to identity, then n should divide this k, and then we have a, because we have to order of a this group, and then we can order of a this should divide the power of this is equal to identity is divided by n. So, by this result we can easily say that in this form we can say simply if we have a order of x is equal to n, then order of a phi of x divides n. So, this means this can be written to this form. So, this is proof is very trivial by using this, and then we using the part A, and then we have to using the previous one. So, we can simply say that order of a phi of x n divides n if order of x is equal to n is there preserving. Okay, now I just this section, you know that I conclude with this example. You know this consider two groups Z and R star is a set of a non zero real number, and phi is a map from Z to R and defined by whenever one x is even and minus 1 is odd. And this in the last class I already showed that this is a homomorphism. We take a different 4 cases where x and y both are even, both are odd, one even, one odd, and then we have to reversing this thing, and then we have to show that clearly this is a group of homomorphism. Now, I just take a consider in the situation we have to consider kernel of a phi is nothing but is equal to, you have a like this, because kernel of a phi is equal to identity of this set, and then you know that the identity of this R star is equal to 1, because this R star is a group under the multiplication. If it is group under the multiplication, then the identity element is equal to 1. If identity element is equal to 1, if x is the element of z, then phi x is equal to 1, and phi x is equal to 1 means this is equal to kernel f is equal to 2z. Kernel of a phi is equal to, we have a clearly saying to 2z. And now because you see I proved that kernel of phi is a normal subgroup of a G, and then you have a z is equal to this is again is a clearly this z you have a under addition is a group, and we have a 2z under addition is also a group. Now we have to using the property kernel of a phi is nothing but is equal to normal subgroup of a G, and then clearly you see this is a subgroup and this subgroup is a normal subgroup into G. So, this is clearly we can say that 2z is a normal into this z. So, this means by this we can say that into this form. And also if you remember this we have to write if we take another group of multiplication is 0 why the direct image of a R phi z is nothing but is equal to, we have a either 1 and minus 1, and then this is another this is also is a group under the multiplication. So, we just say that 2z under addition is a normal subgroup of this, and now this is clearly this is a G. If we take any group this 1 minus 1 is a group under multiplication, and this is the clearly is a this G is a subset of this R star, and then this is also is a group under multiplication, and then we have to show that this phi z is the set of this. This means this element is under is a clearly is a subgroup of this R star under the set of a non-zero real number. So, this complete the example. We have to try to exploit some into this form. So, I think I have to stop today lectures here to this lecture here. We complete this lecture some basic properties of a homomorphism, and in the next class I continue some more properties of a this homomorphism, and after completing this homomorphism part we move to the another is a part is called is a isomorphism, and then prove the some important theorems of the group in the isomorphism, theorem of isomorphism.